Welcome to Unit 5 on our Chapter 10, Part A. So this is a very long unit, a very long chapter, because it's very important to the role of operations management, in which we will be studying quality control. And what we're going to be doing in this first part is kind of laying a little background, some foundation information that we'll build upon in the other parts of this chapter. So looking at statistical process control from a historical point of view, statistical process control is all about the use of statistics to control processes. Now, statistics for a lot of students is a difficult subject. I want to put your mind at ease here. We're not going to be going very deep into statistics. And the part that we're going to be doing is fairly straightforward and simple. Walter Shewhart, even though his name looks like it should be pronounced Shewart, I think the family preferred to have the last name pronounced just as if there was an E in there. Shewhart is credited with the development of statistical process control around the 1920s when he was employed at Western Electric. You may want to do a Google search on Walter Shewhart to learn a little bit more about him. We all owe Dr. Shewhart a great deal of gratitude because his techniques that he gave us in statistical process control are used today exactly the same way that he wrote them in the 1920s, and that's almost 100 years ago. And it is through his control procedures that allows corporations all around the world to be able to control their processes and therefore keep their costs low, and allows you and I to be able to go to the shopping mall and afford to buy the products and the services that we want to buy at the shopping mall. So we all owe Walter Shewhart a great deal of gratitude. Now, since we're going to be trying to control our processes, we should talk a little bit about the principle of control. Now, it doesn't matter what it is that you're trying to control. There's always two pieces of information in controlling anything. The first is we need to have a definition or some standard of what represents what we're looking for. In this case, it's quality. What is that definition that we're looking for? And this standard or this definition cannot be vague. It has to be very specific. This is exactly what we're looking for. The second thing is we need to have some type of observation, or we're going to use the term measurement, some way of collecting some data to see how we're actually doing. And then we're going to be comparing these two numbers, the standard versus the observation. And if there is a significant difference between these two numbers, then we need to undertake some type of corrective action to have the process go back into control. So, the whole field of statistical process control that Walter Shewhart gave us can be boiled down to answering two fundamental questions. So what I'm trying to do is to just keep it easy so that we don't get caught in the formulas and in the calculations. We're just trying to do basically two things. The first is we're trying to answer the question, is the process capable? And you may ask, capable of what? Well, is it capable of producing a quality product or a service? And we have a tool to help us answer this question. This is a question that's a yes or no question. There's no ambiguity about it at all. It's either yes or it's no. And our tool for answering this question is called a process capability calculation. Now, this will be the last thing that we will study in this chapter, but if we were implementing statistical process control in the real world, this is the first question that we should ask ourselves. So if the answer to this question is no, then we need to improve the process until the process capability calculation produces a result that turns the answer to this question to yes. And once we have a yes to this question, the process is capable of producing a quality product or service, then we can ask the next question. And the next question is the process in control? Or to say that another way, is the process stable? To say it in even a third way, is the process predictable? So all these things are basically saying we have a process that is capable of producing a quality product. It was capable yesterday. Is it capable today? So each day we need to basically re-answer this question, is the process in control? And the primary tool that Walter Shewhart gave us for answering this question is the control charts. And that will be the primary part that we will be studying in this chapter, is the use of control chart. Now, since we're going to be attempting to control processes, let's review a little bit about what a process is. So a process is a series of tasks. It could be one task, it could be many tasks, and at the completion of all of the tasks, that we have some type of output or we have some type of result. Now, to begin the first task, there is some type of input that's necessary. The input, if we were producing a product, could be materials. If this were a service process, the input could be information. For example, if we were processing a loan application at a bank, we would need to have certain information about the borrower, how much money they wanted to borrow, as well as some other information. And the output of each task becomes the input to the next task. Now, the one thing that we know for absolute certainty is that the output, the result of the process, that there will be variability in that. In other words, from day to day, there will be slight differences in the output. Now, let me give you a couple of examples of this variability, something I think that we could all identify with, and that would be going to the doctor. So we're not feeling well, and we go to our doctor, and his job is to help diagnose what's going wrong. So within the human body, there are a number of different processes that take place. We have, for example, a cardiovascular process. We have a digestive process. We have a lot of different processes that take place. So when we go to the doctor, either the doctor or the doctor's nurse is going to take 3 simple measurements or observations to basically get an idea on how well our bodily processes are taking place. And those 3 measurements are going to be, they're going to take your temperature, they're going to take your blood pressure, and most likely they're going to take your pulse. All 3 of those measurements are very simple to do. They don't cost a great deal of money to do that. They're non-invasive, and they give the doctor an idea of basically what is going on. So let's say that the doctor took your blood pressure, and your blood pressure is a little elevated, and so he wants you to come back in a few days and take your blood pressure again. So when you come back another time and he takes your blood pressure, is your blood pressure going to be the same as what it was the original time? The answer is most likely no. So there's variability in the output. There's variability in the blood pressure. So this variability will always be there. As operations managers, what our job is, one of our major jobs, is to try to reduce the amount of the variability. So this variability that's going to always be there. What causes the variability? Well, there could be two major categories of causes for this variability. The first is just randomness. These are things that we have little to no control over. And in our discussion, if the cause of the variability is randomness, and if we have little to no control of that, there's not really anything that we could do regarding the process. So going back to the medical example that I used in the previous slide, your blood pressure will be slightly different from one blood pressure test to another blood pressure test. So most likely the reasons for the changes in the blood pressure is just randomness. It could be you ate a meal that had a high salt content to it, and that elevated your blood pressure a little bit, or something else happened that caused your blood pressure to either increase or to decrease. The second cause of variability is we use the term assignable. When we say assignable, we mean that something in the process has gone wrong. Something in the process has changed. And whatever this change is, this variability is going to continue to be there every time that we take this measurement. It's not going to go away. So there's something that caused this change, and that change is going to stay there until we figure out what the cause is and we take some corrective action. So again, going back to our medical example of blood pressure. So let's say that your original visit to the doctor's office, your blood pressure was elevated, and you come back a second time and it's elevated again. You come back another time and it's elevated again. So now the question is, what is causing this elevation in blood pressure? Well, there could be a number of things that could be causing it. It could be your diet, perhaps using too much salt. It could be a weight gain, which could be causing that blood pressure to increase it as well. So the primary tool that we'll be using for making the decision on whether or not this variability in the process is the result of randomness or an assignable cause is control charts. So control charts is a graphical tool. So they say a picture is worth 1,000 words. So it's a graphical tool. It kind of gives us a picture of what's going on. A control chart consists of two horizontal lines. The horizontal line at the top has a name. We refer to it as the upper control limit, or the three-letter acronym UCL. And the lower horizontal line has a name, the lower control limit, and we'll abbreviate that by LCL. Now there are formulas that I will give you and I will teach you on how we calculate the values of these two control limits. So the first step will be to do the calculation and to calculate what the values are for these control limits. Then we can physically or graphically draw the two lines and label what the value is for each of these control limits. Then we're going to be taking our measurements, our samples, and we're going to be plotting the data with respect to the control limits. So each of these X's represents an observation that is taken in time. So this is the first observation that we took. Perhaps the next day we took another observation, and this was the measured value that we had for that. The next day, we took another observation. Here is the measured value we had for it. The next day, we took another observation. Now, we can see that there is variability in the output. We can see that because the x's that are shown in this chart do not fall on a straight line. If they fell on a straight line, then there would be no variability. But they don't fall on a straight line. So there is variability in the process, which we expect. And then the next day, we have an observation which takes us above the upper control limit. So once we have calculated our control limits, once we have plotted our data against the control limits, then we can draw a conclusion based upon the plotting data. And the conclusion is it. If the plotted data points fall between the upper and the lower control limit, then we conclude that the variability that exists is the result of randomness, and therefore the process is in control. So for the first 4 days, we see that the data fell between the two control limits, and the process was in control for those 4 days. But for the 5th day, we see that we have a data point that falls above the upper control limit. So if that occurs, then our conclusion will change. Our conclusion will be then that the variability is the result of an assignable cause, and therefore the process is not in control. Now, the assignable cause that caused the last data point to fall above the control limit, the control chart does not tell you what the assignable cause is. This is where we need to use some of the techniques that we studied in the Management of Quality chapter to go through an analysis of what has possibly taken place, what's different between what happened this day versus the previous day, and to identify what could be some potential causes for this assignable reason. And once we've identified what the root cause is, take the corrective action, and if we do it correctly, the process should go back into control. Now, when we take our measurements, when we decide what the data is that we're going to collect, there are 2 types of data. And for each type of data, there is a specific type of control chart that is used. The first type of data is referred to as variable data. The definition of variable data is data that can take on many different values. So the example that I've been using in this part regarding blood pressure, that would be an example of variable data. So your blood pressure varies, could vary, it could take on any number of different numbers. So if our measurement is variable data, then the control charts that we will use for this type of data is the mean chart, and there's another name for the mean chart. It's also referred to as the X-bar chart. So X-bar or mean chart mean the same thing. And the other is a range chart. So we always need to have both of those charts if our data is variable data. The other type of data that we could have is attribute data. The definition of attribute data is this is data that can take on just certain values. And there's 2 types of attribute data. There's one type of attribute data where the data we measured, things are either good or they're bad. We refer to that as binary. There's only two possible states. It's good or it's bad. And if the type of data that we're taking is this type of data, it's either good or it's bad, the control chart that goes with that type of data is referred to as a P chart. And the second type of attribute data is when we are counting the number of defects. So when I'm counting, I start with 1, 2, 3, 4, 5. So the data can take on certain values, integer values, okay? Starting with 1, it can go up to any number. If this is the type of data that I am collecting, the type of chart that goes with this type of data is referred to as a C chart. Now, as we go into the other parts of this chapter, we'll be using a case study in which we will show the different types of data, show examples of this data with respect to the case study, and do the calculations and plot the control charts and draw our conclusion. So this will conclude part A of this unit.